Thank you very much, Lawrence. It's a real pleasure to be here, and I feel a special kinship to be in Britain, because I took my advanced degree in conservation at York University, the Institute of Advanced Architectural Studies. So here we now move forward. And in my talk, I'm going to be talking actually quite a bit about modern buildings. By modern, I mean built in the last 50 years or so, rather than just looking at things historically. But I'm going to be making a crucial comparison. As you've seen in the last 4 or 5 months, we've had a series of earthquakes, and one in eastern Turkey, in Van. What are the images that are coming out? They're concrete buildings. Not only have they fallen down, it's really with concrete frame construction that the term pancake collapse was invented, because the floors are so strong. And of course, when they do fall down, it's very hard to extract the survivors, because the floors, as you see here, often very thick, are so hard to even drill through. The Van earthquake reminds me of the 1999's earthquakes further to the west in Anatolia, where it's building after building on the ground. And then very soon after that, the one in Sikkim, in the Himalayan chain in North India, which extended with damage in Bhutan and in Nepal. Same thing, concrete buildings. Now, it's really interesting to look at the professional reconnaissance report that was done by an engineering team, and I do know one of the engineers on this team, the Indian engineers who went there to look at it. And this is really important to notice that not only are they observing that the reinforced concrete buildings don't have earthquake-resistant features, and remember, the Himalayan chain has been identified as an earthquake hazard area for generations. They don't even have structural engineers in that part of the country. And it's worth looking at what we see there. And I have not been there, but I've, of course, been to India many times, as you'll see. But I looked at on the internet, and I said, well, then what's that? I mean, that building didn't go into the earthquake in good condition. It's certainly older than the one that collapsed. So how do, people say you gotta have good construction and all of that, no matter what the period, but this is lousy construction, and it's heavily deteriorated, and it's still standing. So it's worth considering what we're dealing with here. With historical buildings, of course, by definition, they've been around for a while. So in this report, they recognize that this traditional ECRA construction, they call it ECRA there, which I think is actually, from what I could tell, a little closer to wattle and daub medieval construction here than to infill masonry. But never mind, it's easy to then keep going and realize that schools are one of the most vulnerable assets we have, and it puts all of the children at risk, whether it's Italy or India or Turkey or you name it. We've had schools being a particularly vulnerable building type. But you'd think that they would do better modern buildings. And in India, there's the term puka and kacha. Kacha for cheap or impermanent construction. Puka is for permanent construction, which is now often identified by people as being reinforced concrete or concrete mid-block masonry. Well, look at what their observation is. The ECRA houses are the ones that performed. Traditional means of construction that this report even advocates be resurrected in this area and put alongside of, at least, of modern concrete construction, which itself should be improved. Now, my work on this subject really began with my being in India on a fellowship to document the mills, in fact, there, the working factories in India as a photographer, when I fell in love with Srinagar in 1981 and discovered they had a very traditional form of construction, and even it seemed almost a medieval way of life, much of which is rapidly being lost in these days. But here you see the traditional construction in these narrow streets. And I'm not going to dwell at length on this because I've spoken of this before, and this book is now published by UNESCO, where I go into great detail about the earthquake resistance of the kind of construction that I found there. And I came up with this name because what I really came to realize as I worked on this subject, that traditional is modern. And that's the insight that I feel I have. We're not anymore, should we use the term archaic construction when we're dealing with this, because it has so much to teach us in terms of how we even improve our current forms of construction. So moving on, that's one of the pictures that I shot in 1981. And I often have shown this at the beginning of a talk and say, you know, how can you ever believe that this would be earthquake-resistant construction? Never mind, is it even resistant to static failure? So, and when you get into it, you even see that the masonry piers do not line up, which would be anathema in a bearing wall masonry building. But this is bearing wall masonry, and by all calculations, that would be a soft story. And so the timber is so critical here. We are dealing, in fact, with reinforced masonry construction, but coming from a building tradition that goes back hundreds of years in an area of northern India where timber does exist, does grow. It's a mountain climate, and the Vale of Kashmir is a fertile plain. The reason why these buildings were there is because it was a fertile plain, but it was a prehistoric lake bed, much like Mexico City is a lake bed. And so this is an extremely soft soil site. This construction was not invented for earthquakes, I believe. I don't have any proof one way or the other, but it was invented for building buildings that would last on a soft soil site. And that's why I think we're seeing the timber armature there. And you can see the effectiveness of this when you realize that this building here is a bearing wall masonry building. It's not a veneer, it's not a frame structure. So how is that done? And this is what I determined is the way those internal frames work. They've been even very effective in creating, through just the weight of the wall, a tie-in with a floor diaphragm, which is all, of course, appropriate for contemporary construction today. And that's where they fit, above the windows and at the floor levels in many of these structures. This, I determined the best word they had for it was talk construction, which was not exactly an engineering term there, but I found no other. It was just seemed to be a construction technique that people did. Looking at the buildings, we're not dealing with short buildings here. They went 3, 4, 5, sometimes 6 and 7 stories, and these are bearing wall buildings. This one here, you can see where the floor beams are extending through the wall and being sandwiched between the timbers front and back of the thickness of the wall. Absent this kind of structure, you can see that the buildings tend to come apart just from the soft soil site. And in 1888, there were historical records where visiting British travelers commented on the earthquake that they experienced, that these seemingly rickety, tumble-down buildings had resisted the earthquake, whereas the palace in the more British style of unreinforced masonry had fallen down. At the time when I discovered this, I'd never myself investigated earthquakes, and therefore I'd not been in a reconnaissance, I'd not really studied contemporary earthquakes. That has come in the last 30 years since I first went there. Turning to Nepal is very interesting because they don't share this building tradition, even though they share a part of the real estate of the mountains of the Himalayan chain. You see an example here of how the whole building in Srinagar is leaning as a unit, and here in Kathmandu, where the absence of having that kind of ring beam or a tie around the whole building, the building tends to come apart. But even more profound was how an earthquake in 1934 affected the buildings in Nepal. This may be familiar. Kathmandu is a tourist area, and those of you who did remember Patan village, it looks a little bit like this, but were you really aware of the fact that in the 1734 earthquake, that very same view looked like that after? All of it has been built back again. And from what I understand, the first rebuilding campaign also did not introduce seismic features into the buildings. They are unreinforced masonry today, although some of it have been subsequently retrofitted. Interestingly enough, this form of construction is honored in the current building code in India. And you see here an example of the drawings showing that. But what I found interesting, and some of you who've been involved perhaps with India may know Professor Anand Arya, who was instrumental in getting this material into the code and recognizing essentially what they call rules of thumb for traditional construction, non-engineered construction as they call it, in India, because it's so fundamental to the housing the people. But for some reason, they don't recognize the floor capture, the double layer of timber with the joists and the beams coming through. And I've never been quite sure why. In my conversations with him, I think it was just something where they had not, they would themselves know it, but hadn't really gotten into that level of detail. So the other system is known as Daji Duari, and this is a much more appropriate term to the system. It's it comes from their textile industry background, patch quilt wall, from what it looks like. But that's really interchangeable with the English term of half timber. So, and you find Fachwerk in Germany and Kalambage in France and so on. Almost every society in the world has a version of this form of construction. Is it specifically earthquake generated, earthquake resistant? No. My belief is that in an area where wood was available and reasonably inexpensive, this becomes a very inexpensive form of construction. It's for socioeconomic reasons that something like this would develop, just the way it did in Suffolk and Norfolk and in Britain, because just think of the efficiency of only having to build one single leaf of brick is all that this contains, just as it often, I think, in the medieval construction here. So this dates back even beyond this picture. This is ancient Rome. It was dug up in Herculaneum after it was buried by Vesuvius. These are buildings that generally have not survived 2,000 years, but here is one that was restored when they found it and is recognized perhaps by Vitruvius, but I even sometimes doubt that what they've ascribed to this is the correct term. But it's the same thing here, filled with stone. And when you see one of these buildings, this is a demolition, not an earthquake damage, opened up, you wonder how could this also be an earthquake-resistant construction? It's so gossamer thin. It's lightweight construction. Yes, the weight of the building is much less, which of course is an advantage and plays a role. But the resistance of these buildings has proven to be greater than that alone would be the reason. When I was first there, building construction in Kashmir was often still done this way, but most of the buildings, even at that time, were reinforced concrete. And what people wanted for a pucca house would be reinforced concrete. Uninsulated, unheated, you froze in this thing, whereas the old mud-mortared buildings did much better, I think, in terms of the environment, but that's what people would want. Now, the first demonstration that in my lifespan where I could look at the performance of this in the field was, of course, the 2005 earthquake in Kashmir, which the epicenter was in Pakistan, and I'll get to that a little bit later. But on the Indian side of the border, in Baramulla, I did find this example, and you see that the Daji floor only at the top, whereas unreinforced masonry below, that floor formed a bridge over the failure of the wall below. Again, interestingly enough, it is recognized in the Indian Building Code. But like the other one, it doesn't talk about the floor diaphragm connection. Now, one of the first and one of the very two examples I have of where this is specifically an invention to resist earthquakes is a product of perhaps Europe's most famous earthquake, not in Italy, but in Portugal, the 1755 All Saints' Day earthquake. It happened when everybody was in church. So you can imagine when the churches all caved in and killed their occupants, how this became almost a mystical event. And looking at the science of it was probably the last thing on many people's minds. And then it was followed by a fire. And then that was followed when, after everybody ran out of the area that was burning down to the pier to take boats across the harbor, a tsunami came in and drowned them. So it was this 1, 2, 3 punch that just turned this into quite the event for all of Europe. After that earthquake, the Marquis de Pombal, who later became the Marquis de Pombal, who was the king's right-hand man at that time, was engaged or took on himself the task of getting all of the best minds, all of the best engineers in Lisbon together to come up with a system that would be earthquake resistant. Interestingly enough, what they chose to be that system is infill frame masonry, just like I showed you in Kashmir, and not unlike Fachwerk in Germany or half timber in Britain, but a very robust form with double X's in it. And the area, I believe, there's not really very good records on this. I believe what they did is they simply did an empirical study. It's not a mathematical study. It's an empirical study, as we often do, like EFA teams, to earthquake areas or other reconnaissance teams. What you do when you go and you gather the evidence from the earthquake. And what did they do just walking around the city? They noticed the medieval parts of the town that had half timber construction didn't fall down. But the unreinforced masonry buildings did, and the churches certainly did. Well, interestingly enough, in just the last few years, the government of Portugal and the engineers working on a government funded project took out some of these frames from buildings that were being renovated and the frames were being lost, and put them on a stress test, a pseudodynamic test machine that they have in their government lab. And this is the hysteresis loop that came out of one of those tests. And this is probably the most, in this particular case, the equipment got to the end of its thrust before it ever got to the limit of the strength of the specimen. So this is the kind of equipment. So the performance of this is seen with a tremendous amount of damping effect in it, of hysteresis damping that comes from this material as it's moved back and forth in the earthquake. Now I'm going to just take you very rapidly through a series of earthquakes that I've been able to visit and see the results from. And of course I mentioned before the one in Western Turkey. But tucked in among these buildings were buildings that were often not recognized or put in the reconnaissance reports, as particularly my colleagues in EERI in the US had come back and I say, were there any timber frame buildings that you saw there? And they say, well, there were a few. I saw them, but did you take pictures of them? No, I wasn't interested. We were looking at concrete and so on and so forth. So I got on an airplane and went over and had a look, and here's a 3-story one. And there's no way you would classify these buildings, even in their original construction, never mind current 100-year-old or 75-year-old. Very often these buildings look older than they are. Condition as good construction, as at premium in terms of craftsmanship. They were built by people themselves. They were not built by people who'd gone to school in construction or by companies or engineers. This is non-engineered construction. And what you're looking at here is not a building that was damaged by the earthquake, but one that had the back wall quarried away for building material because it had been abandoned for something like 30 years, 20 or 30 years. And it was in the heart of the damage district. The earthquake couldn't take it down even when it was in this condition. An example from another photographer, everybody says, well, the concrete building's ever so much bigger. So we're dealing with, there's a scale difference. You have little buildings and big buildings. How can you condemn the performance of the big buildings by example of the little buildings? Well, we've seen small buildings also, concrete, have not done well. And next to them, here is another one of these in Turkish, known as humush construction. Well, it's one thing to go around as a reconnaissance photographer and looking at these things on the fly, but there was a research team in Turkey that did a quantitative study. And they, in my mind, unfortunately, lumped together all traditional buildings, including unreinforced masonry construction, into the bars you see on the right, and on the left is the reinforced concrete frame buildings. So embedded in these bars on the right are the humush buildings, probably more on the bars even with better performance than other traditional buildings that may not have performed so well. So we have one example here of a family I ran into when I was in Düzce. This man had started construction on a reinforced concrete new house for his family. And they were living in his house his father had built, which is seen there. This is after the Düzce earthquake. And he stopped construction when he saw that the concrete buildings in Düzce had collapsed and built himself a humush-style new house. I thought this was a remarkable example of how people learn and how a tradition can be resurrected when an event as rare as an earthquake comes through and affects it. In Gujarat, 2001, that's Anjar after the earthquake. Bhuj after the earthquake. A mixture of traditional and contemporary concrete buildings. The traditional buildings were a form of dressed and rubble masonry that had no timber armature in it, and it was heavy and a lot of it collapsed. But you go to nearby Ahmedabad, which was also in the damage district, and you find timber lacing of both types that you found in Kashmir. And in Ahmedabad, if the concrete building was built subsequent to 1992, it had a much higher chance of collapsing than if it were built before 1992, as counterintuitive as that might seem. And that was for a simple reason. They made a zoning change that gave them a more floors credit if they put parking underneath. Excuse me? I mean, and this had historically been an known earthquake area. In fact, the earthquake return period there had been remarkably frequent for an area that was mid-plain. So you see, half this building had collapsed in a pancake. The other half is effectively destroyed. The bottom columns, it was scary even to go under there and have a look. Why the difference? Well, there was a cultural flow of construction tradition that flowed into Islamic Ahmedabad of the Mughal period that didn't really go into Hindu Bhuj. And it's not a religion thing, it just seems to be cultural byways and highways flow. But there was a Hindu sect that had their home temple in Ahmedabad, known as the Swaminarayan sect of Hinduism. And they had built a building in the Ahmedabadian tradition in Ahmedabad. And they then also had a temple complex in Bhuj, and they used the same Ahmedabadian building tradition in Bhuj. So here we have a dramatic example, and you'd think that was even a soft story just waiting to collapse. This is infill masonry in those upper floors. And the concrete temple or pavilion in front of it collapsed. Moving on to other earthquakes. This is the one I mentioned before, of course, on the Pakistan side of the border. And as you remember, very large apartment complex, a large part of it collapsed in Islamabad, which was remote from the damaged district. And you have these heartrending pictures of people trying to be saved from underneath, the ones that didn't get squashed just from the collapse. So Balakot was devastated. And as you can see, it was largely a dressed stone, but each stone was almost like a cube rather than a rectangle. So very little bonding to these walls. But as we went around there, it was very interesting. I'm just going to show you one particular experience we had going very deeply into the remote countryside, way away from where government assistance would normally get to until weeks later and all of that. And we found this one little rural village up on the top of the hills where people were living in tents. And their houses had collapsed. They were largely of rubble stone, and their own store, built, which would be the premium building in the town, had a soft story collapse. But the house there looked undamaged. And we looked and investigated this, and it was a dodgy construction, dodgy Diwari construction. This is another building that was near the town. That was a store. Shops all across the ground floor, and the building is still standing. And you can see the limits of the earthquake damage right there. So what happened when people saw this? This one family, for example, lived in this house that you see there with the rubble stone. And there on the left, you see the owner and his carpenter. They rebuilt their house in dodgy construction. The mountain form of traditional dodgy construction is more of a stud frame with these small, short pieces and tiny panels, which I think is evolved out of the fact that they use rubble stone as the infill. So the smaller the panel, the more frequent the timber reinforcing, you get a very good holding of the system together. And the amount of damping that comes from this in the event of an earthquake would be quite large, and the chances of the building falling down from the panel falling out are even less. People were proud of this. The government had told everybody that they would get financial assistance if they built in reinforced concrete or concrete block according to the rules that had been established by their engineers. And if they built in any other system, they would get none. At the time we examined this, it was about a year after the earthquake, they went ahead and built anyway. At that year point, the government approved after several of my colleagues in NGOs had been campaigning to approve this form of construction. I show this picture because this fellow is even deeper in the rural countryside. And there's something really wonderful about the poise of this fellow. I mean, he probably has not spent a day in school. He's never been trained in construction, presumably, but he's rebuilding his own house in this way. And I kind of see a wisdom in his face. Not knowledge, but wisdom. And I think that that's what's so profound about getting into this level of seeing how people relate to their environment and then take control of their own recovery. And the government of Pakistan, to their credit, finally recognized this. And then my colleagues in the NGOs put together, particularly this architect from Switzerland, Tom Schacker, who is now in Haiti doing similar work, put together a manual of practice for improving the detailing of these buildings, but working within the tradition that he learned from them. I think that's what's so important, that it's a two-way conversation. And here you see some of the lessons undertaken with these rural farmers, basically. And they then, 1 year later, approved the bearing wall system, which there in Pashtun is known as Batar. And so these are new houses, over 200,000 new houses in Daji have been built, I've been told, by UN Habitat. So I want to conclude the talk back from big to small here, and just leave you with the experience I had in rural Turkey, where these little villages in an earthquake that was 6 months after, and a year after the big earthquakes that you've all seen or read about in Western Anatolia, the Orta earthquake of 2000. And I happened to be driving to go see the historic city of Safranbolu when this earthquake happened. I got a phone call on a cell phone, and I got there within less than 24 hours of the time when the earthquake happened, and have pictures of these houses, which are of traditional Humush construction. Well, the government officials and inspectors came in and persuaded the occupants of this town that their buildings were essentially destroyed and they're better off tearing them down and moving to new houses that they will fund. And in a neighboring town, but then there were two towns this happened, this is the subdivision the government built, because the geologist said that this site was safer than where the village was down by the creek. No barns, no place, and not even an agricultural soil left on the site. And they put these houses here, 80 houses, that the poor owners were persuaded to accept as a program for rehousing them, and even partly pay for. They were never occupied. Only 5 of these houses, 5 years after the earthquake, were occupied, and the population had risen to 7, and 2 of them moved back to the village. Because there was no mosque, there was no store, there was no place to put your animals. On top of that, that was the system of construction. Unreinforced masonry, hollow clay tile block with a heavy concrete roof. Excuse me. How did they get from a good performing, dodgy construction to think that this is better? The reason is that these inspectors looked at the debris field of all the plaster falling off and the movement that these buildings did, which I consider to be their way of resisting earthquakes, which has to create damage of that kind of nature, and saw it as they're being destroyed. But nearby, these are the gentlemen of the village. All the people in this village were over the age of 50 or 60. They weren't able to farm really anymore. All the young people had moved to the city. But there was another village 20 miles away in the same earthquake. And that, within my first visit, this is my picture of the family having come out of their house because of the damage, the same kind of damage you saw before, which you see there. They were scared of it and they were in a tent. But these were younger farmers. They spurned the government edict that they should move and repaired their houses themselves. And I came back to find them having moved back into it. And this is the change these houses went through. So what the problem is for disaster relief people is the disasters are so far apart that it's a whole new host, a whole new generation of people with each one. And the learning process, I think, the passing on of this kind of aha moment, oh, that maybe that isn't good policy, does not happen. They start over again, and with the best of intentions, produce something that takes away more than it gives. And I think that I want to leave with that observation from all of this. We're back down to the people in the village who, in the end, in order to recover, are best able to recover for themselves, to rebuild their own houses. And we can look on and learn from them, and then give back something after we've learned. Thank you very much. These are 3 websites. All of my papers are open access and research all the way back with some pictures of the mills as well on the top one. The next one I created for the UNESCO book on Kashmir, and the book is available. It's printed in Britain as well as in the United States. It can be ordered from online retailers. And the HaitiPatrimoine.org, the book I show you here, is available as a PDF for free by a link to the World Monuments Fund website, and the World Monuments Fund has printed it and published it.